Good afternoon, ma'am. This is Kulbhushan Patel from second year CSC Core branch. Today I'm going to present a PPT on the topic application of finite automata in networking. So we will start by application of finite automata. So what is finite automata? We are now devoted two chapters to the study of finite automata and will conclude both simply and fairly advanced usage. Example will be taken from the theory of operating system, data communication, and network protocol analysis. We begin with a few very easy examples. And my goals for this chapters are: at first glance, this chapter might seem a bit much for a student. A casual inspection will reveal that it covers a number of topics, including first stages in a process, second creation and persistence of an object in graphical system, third process management in time sharing operating system, fourth parity checking on a bit serial communication line, and finally connection management for the transmission control protocol. Each of this topic might easily cover a few weeks in separate course. Some such as management of TCP will readily justify an entire course. The purpose of this chapter is not to teach this topic, but to show the utility of finite automata in many areas of life. The author of these notes now faces a problem: how much to say about each application being discussed. The original draft of this chapter comprised only of finite automata, labels of each state and transition, and few comments. The idea behind this presentation was just look at the picture and note how many uses there are. This approach was thought not to be sufficiently so. The revised chapters add some explanation when thought useful. We begin this chapter of illustration with the remark that finite automata can be found everywhere. Traffic lights, vending machines, and washing machines. Both dishwashers and cloth washers. One of this author's friends, an MIT graduate, claimed to be claimed to be able to model a baby as a finite state machine. But this is a probably a excessive zeal on his part. On his part. So the author has given us a example of a washing machine here. A basic washing machine is easily modeled as finite automata. Now that you understand finite state machine, you can get really clean clothes. Like you can do like start, then fill, wash, spin, rinse, fill again, agitate, spin, done. Your clothes are done like that. Okay. Next. Process through the computer science curriculum. It is not common to view a process in terms of finite state machine, but it can be done like this: a sequence of courses in the CS curriculum. One should note that finite automata are not often used to model processes such as this and the next one for the reason that other models usually do it better. Nevertheless, we can view each of these two as two finite automata, although with fewer transition than its usual. Life cycle of internet student is here. The student of the internet is published standard as a way to agree on rule for running the internet. Each standard goes through a life cycle, beginning as an unofficial working copy and ending as a historic document. Here is a finite automata modeling that process. First is the internet draft. Internet draft is a working copy. It is a work in progress with no uh, ethical standing. Second is request for comment. If a internet draft sufficient sufficient promise, it is edited and published as a RFC, request for comment. At this stage, other interested parties are invited to comment. Third is proposed standards. When the RFC becomes stable and is well understood and is deemed to be of general interest, it becomes a proposed standard. Fourth is draft standard. Draft standard. A proposed standard is elevated to a draft standard upon the completion of two unsuccessful independent and interoperable implementations. The fifth one is Internet standard. Upon demonstration of more successful implementation, the RFC becomes an Internet standard. And the last, historic RFC. Historic standards are either old Internet standard that have been suppressed or other drafts of sufficient Internet to merit keeping. Defining a line by 2 points. We can define a line by 2 points. How? Just make it put some 2 points and make a line between them. We now consider an example from object-oriented computer graphics. Recalling that 2 points specify a line, we consider a line segment object as being the line between any two specific line. We consider a line segment object as being the line between any 2 points. There's we have a diagram over here how it's possible and not. The line segment is defined by two distinct endpoints and comprises all points on the between those points. In our example, we have a line segment from point on the line between those points. In our examples, we have line segment from point from 0 comma 0 to point 2 comma 2, which can be modeled by the equation y is equal to x, with 0 being less than x and x being less than 2. Note that the point 1 comma 1 is on the line segment. The point 6 comma 6 is not on the line segment. Although it is on the line defined by the equation y is equal to x. In this example, the code for the line segment object has three methods. First, a new method to create an empty instance of the object, that is with no data members defined. A point x comma y method that specifies one of the 2 points for the instance of the line segment object. One call this method twice to specify the line segment without making distinction between 2 points. A point x1 comma y1 x2 comma y2 method that fully specifies the line segment distance. The design requirement for the line segment objects calls for it to be specified by two calls to method point x comma y, or a single call to point to x1 y1 x2 comma y2. Either point 0 comma 0 followed by call to point 2 comma 2, or point 2 comma 2 followed by the call point 0 comma 0, or a single call to point 0 comma 0 to 2 comma 2. The design requirement for the line segment object calls for it to be specified by two calls to method point x comma y, or a single call to point x comma y1 x2 comma y. Either point 0 followed by call. For those when when the line segment has been specified completely, the instance of the object can be persisted, that is stored in database for the graphic system. The problem that this finite automata model addresses in that of storing an incompletely specified line segment. If we create a new line and specify only one point by a single call to point x comma y, we do not have a complete description, and the line segment instance should not be persisted. An example from operating system. We now consider process scheduling by system running operating system running in time sharing model. In the theory of operating system, the term process is to basic that is impossible to define exactly. So just think of its problem that is running and using the CPU. There are three possible events that will cause a program to stop running. We consider only two. First, the program terminates after finishing its computation. We ignore this generally. Second, the program requests IO input and must wait for the completion of the IO, or the program must avail the completion of an external event. Third, the third, the program times out. In this sharing modern operating system, allocate to each program a set amount of the called a quantum, after which the OS stops running that program. OS stops running that program and allocates the CPU to another program that is ready to run. Here is the finite automata for the scheduling process. This is the finite automata for the scheduling process. If the process is running and exerts its time allocation, it times out and is marked by the operating system as ready to run. The operating system maintains the list of program ready to run. The operating system maintains the list of program ready to run. Run is a queue and dispatches the next in line. That is, allocates the CPU to the process and places in the running state. If the process is running and must wait on an event, it is placed in the blocked state. Upon completion of the external event, the process becomes ready to run. Process becomes ready to run and is moved to the ready state, from which it will eventually be dispatched. Process in either of three principal states can be suspended. The two button state deal with the suspended states, not of much interest to this author. Next, we have parity checker. We now consider the problem of checking the parity of a transmitted hit stream. The term parity generally applies to a binary bit stream and reflects the number of ones in the bit system. The parity is odd if the number of ones is odd and even. If the number of ones in the bit stream is even, remember that 0 is even number. The principle behind the parity detector is a pair of simple rules. Even number plus 1 is equal to odd number. Odd number is plus 1 is equal to even number. We model the parity checker as a Moore machine with an accept state indicating that the received string has the proper parity. The events causing transition in the finite automata are the receipt of 0 and receipt of 1. So we can see here even plus 1 is equal to odd and odd plus 1 is equal to even. Even plus 0 is even and odd plus 0 is odd. This is the diagram to depict that. For those with experience in hardware design, the circuit can be implemented by single flip-flop with a synchronous present to clear the flip-flop to 0 at the beginning of the string. As an aside, we show how to extend the standard 7-bit ASCII number code to an 8-bit ASCII code with parity. This is the only one of many options for data transmission. In this scheme, the number of ones in bit 7-bit code is computed and a parity bit added to make the parity correct. So now we are going to do modeling of the TCP. So in that model, the TCP is a protocol used in connection with IP, have TCP IP to control interaction between a TCP client and a TCP server. More generically, the two communicating TCP program are called TCP hosts. But we shall consider the special case in which it is easier to speak of a client and a server. A communication protocol is a set of rules or conventions to be followed by the two or more communicating entities. For example, there is the telephone protocol. The telephone rings and one answers hello. To initiate the transfer, what we see in this telephone protocol is called a handshake. In many areas of computer science, two devices pass initial data in order to set up communication link using an angel protocol. The conceptual model of communication via TCP is shown in the next figure. In general, the function of TCP is to allow a client application to communicate with a server application. The communication could be direct, in which on which case both in which case each application will be required to have a complete set of communication software installed. It is considerably easier to allow the TCP layer handle the communication and for the client and server to communicate only with TCP using standard API. So here's a diagram for that also. Client application to TCP client to internet and TCP server application. We now use a familiar application to reinforce the concept just mentioned. At the end of the semester, the student will want to know his exam grade and final course grade. The most efficient way to do this is for the student will call the grade information server using a cell phone. We are very comfortable with the use of cell telephones to communicate. Most of us having a long history using POTs, POTS. We say things like I will call when we mean I shall use my telephone since they will have established reliable communication to be successful. It is the same with to communicating process. The client application communicates directly with the client TCP, the server application communication directly the server TCP, and the TCP processes manages the communication link without intervention for the application. We might we might as well mention a few issues with the nomenclature. The first is that the term TCP is used not only in the protocol itself, but also for the software that implements the protocol. The second issue is that we often hear the term TCP protocol, which translated literally as transmission control protocol. Reluctancy, but then again, we often use the term pizza pie, which office literally means cheese pie. TCP is connection-oriented protocol, by which we mean that the TCP client and the TCP server set up a reliable connection between the client application and the server application. The connection is managed by what is called handshaking procedure. The setup by a three-way handshake and the tear down by four-way handshake. The three-way handshake between TCP client and TCP server application, which tells TCP server that it is ready to accept a connection. It does this by issuing what is called a passive open. It now awaits communication from the TCP client. First, the client application issues an active open to the client TCP. The client TCP then sends a packet to the server. TCP to announce its wish for communication and includes information about its ability to communicate. Second, the server TCP responds with two packets. First, an acknowledgement of the request of the client server, and B, a packet containing information about its availability to communicate. The client TCP responds with packet acknowledging the TCP server pocket packet. TCP client everyone. Here is the finite automata representing TCP client. Remember that the TCP client is the part of TCP program that connects the client software to the internet, handling the communication via the transmission control protocol. This is the flow diagram of a TCP client. First, the TCP client starts in closed state. Second, in the closed state, the client receives an active open request from the client application program and sends a S1 signal to the server TCP and goes to S1 send. Since send, in S1 send, the client either times out and returns to closed to receive S1 plus ACK, a combined signal from the server TCP, and goes to the data transfer state. The client remains in the data transfer state until it receives a close request from the client application, in which case it sends an FIN to the server TCP and goes to FIN1. In the FIN1 state, the client TCP awaits the ACK from the server TCP. When it receives the ACK, it goes into FIN2 state. The FN1 state, the client TCP awaits the ACK from the server from the TCP. When it receives the ACK, it goes in. to the FN2 state. In the FN2 state, the client TCP waits for the TCP server to close the connection. It does by sending a FN. When client TCP receives a FN, it sends an ACK to a server TCP and goes to the time wait state. In the time wait state, the client TCP sets a timer and for it waits for it to time out. It does this at a value sufficient to allow duplicate IP packets to arrive at their destination. When the timer expires, the client TCP goes to close state. So this is a TCP server diagram over here. We can clearly see how the TCP server works. So data to close wait, last account, and in between they have also shown us what is going on between. The server TCP starts in closed state. Second, the server application sends a passive open to the server TCP, which then goes into the listen state. While in the listen state, the server TCP can receive a S1 signal from the client TCP. It responds by sending a async combo and going to S1 record and moves in data transfer state. In the S1 record state, the server TCP receives an account from the client TCP and moves into transfer state. When the client TCP wants to close the connection, it sends a FNs to server's TCP at a time which the server TCP replies with an account and moves to close it. The sixth step in this is the when the server TCP is in the close wait state, it it waits until it receives a close request from the server application, and which time it sends a pin to the client TCP and goes to the last ACK state. In the last ACK state, the server TCP is awaiting the last ACK from client TCP. On receiving this, it goes into the closed state. The four-way handshake reflects the fact that the client TCP will end its transmission to server TCP before the server TCP drops its communication with the TCP line. The client stops asking for information a bit before server stops sending it. The client application issues an active close to the client TCP, which sends a FINS packet to the server TCP. Second, the server TCP acknowledges the request to close by sending ACK pack to the client TCP. The server TCP continues to transmit data until it is finished. When the server TCP has no more data to send, it sends a PIN packet to the client. The client TCP sends an ACK to the server TCP to acknowledge the PIN. Passive open. When the TCP server is in the cloud state and receives a passive open, it moves to the listen state without transmitting anything to the client TCP. Active open SYN. When the TCP client is in the closed state and receives an active open, it transmits an SYN packet. It transmits an SYN packet to the TCP and moves the SYN sent state. The SYN sign plus acknowledgement. This probably should be labeled as SYN S1 to allow that the TCP servers receive and SYN and app replies with a packet containing both SYN and ACK. SYN plus ACK slash S1. This is probably should be labeled as slash S1 as it shows that the TCP client does does what the TCP client does when receiving a packet containing both S1 and ACK. The reader should note that neither the TCP client finite automata nor the TCP server finite automata is complete. Neither have transmission to handle error condition. We repeat the earlier disclaimer. This is not a course in TCP, just an illustration of finite automata. Thank you, ma'am. This is my presentation on finite automata in working of network. Thank you.